back in business. So, ladies and gentlemen, I want to talk about the this issue of evidence, this issue of data, etc. Okay, and this is going to be a brief presentation, but it may open some discussions. Mostly, I hope it will situate you when you think about this issue of evidence and these models. How do they fit together, particularly quantitative evidence? Well, there's basically a set of different ways. So some evidence from the world we end up placing into the model in the form of what are called model parameters. These are assumptions which we encode in the model. And I'd like to illustrate them because I'm hearing some great questions. So where are the assumptions in the model? How are they placed in mechanically? Okay, now here it is. Here's AnyLogic. We could go take a look at one of these models. Maybe we'll take a look at this pertussis ABM model, which I suggested that you might think about building. Let's take a look at this simulation here, okay? This is an experiment. This is a particular scenario. And you'll notice that there's a set of parameters that are specified here of different sorts. You can actually sort these into sort of categories, and Winchell in his inimitable fashion has contributed there, okay? So initial population size, are we performing vaccination or are we viewing it in the pre-vaccination era? Some things about the interface, but also some assumptions about how frequently individuals bring infections into the population from outside the population. Say travelers who travel worldwide pick up, while in Netherlands pick up pertussis, for example. Disease mechanisms. Here we have a variety of parameters that were originally specified in a modeling paper, as well as which relate to loss of immunity, etc., as well as things like probability of primary vaccine failure. We could go for a given scenario and put in an alternative assumption about this parameter. Let's take a look at that. Probability of primary vaccine failure. Where is actually that used in the model? So that number goes in. Where is that, in fact, used? Probability of primary vaccine failure. Well, one way to determine that is to search for it. Probability of primary vaccine failure. Here we go. And we just did a search. Here's our search window. And we find, okay, there's the name of it, and then at the level of a person, it affects a couple things. And one of them is what goes on here. So here, we are actually performing a vaccination event where that probability of primary vaccine failure is actually being used to determine the likelihood of success. And I'll show that by going, here we go, functions, and there's a thing called event vaccination. And here we are saying, okay, we're delivering a vaccine dose, and it has this probability of failing. So delivery of vaccine dose here is something which, with that probability, will in fact not, so if that occurs, they won't be affected, otherwise they'll be vaccinated. So it will transition someone to this state, to a state of being vaccinated. They'll receive a vaccination message, and they will end up here transitioning in their underlying state of protection from one state, say from this susceptible state to this vaccinated state. So it'll transition them as a result of that message. So there it is being used to determine the probability of a coin flip turning up heads, in which case it will, so if it's a vaccine failure of 0.15 with 85% probability when they're delivered a vaccine dose at 2 months, at 4 months, at 6 months, if they in fact delivered that dose, if they present for vaccination and it is delivered, they will proceed to get vaccinated, and that will boost their vaccination, the level of vaccination or degree of vaccination. So that's how that plays out. That's an example of an assumption in the model. And that assumption in the model could be varied. It could be varied on a per scenario basis by having an alternative assumption about that. So we could create a scenario where we have an alternative assumption about the probability of vaccine failure. And many of the things that, for example, Ellen was running as scenarios, we're altering our assumptions about that. Same thing with incubation rate. Here we're assuming that the incubation period for a certain level of a person with a certain pre-existing level of protection will be somewhere between 10 and 21 days with a mode time of 14 days. So those are examples of assumptions. Assumptions either in the form of particular values or assumptions in the form of draws from a distribution where the parameters of that distribution are specified. Okay? So that's an example of a parameter. It's an assumption given to the model. And that is one of the types of ways that models use data. Another way is a technique, and these are two techniques. One is called backing out, one is called calibration. Backing out is similar to calibration, except it's done analytically for very simple cases. Basically here, you're using data from the world that doesn't relate to a particular parameter. It's not data about a particular specific part of the model. And there's a lot of data from the world that's like that. Maybe we don't have neat data on, and I'm going to have to go here, we don't have neat data on, this particular, the timing of this transition. But what we do have data on is numbers of individuals from titers who show evidence of vaccination based on a certain amount of time from when they were vaccinated. Or maybe we have evidence on the number of cases of pertussis in different age groups over time. We can't plug that data into one parameter. Why not? Because it results from a tangled set of different situations or different processes. It's not the number of cases of pertussis over time is not merely a reflection of this one parameter. It's a reflection of these whole set of things interacting. But what we can do is we can match this model against that data. And you saw that with Ellen's presentation. So she had data which she had historically a time series. Sometimes you have time series with respect to multiple ages, for example, that we get from administrative data for diabetic end-stage renal disease or diabetes, and we can match that against model predictions. So there, the model emergent behavior, the behavior coming from the model is being used to match up with real-world data. And it is doing so while we are adjusting parameters that are less well known. So there was a question earlier about which parameters did you adjust for Ellen. And so she said we adjusted 3 parameters involving, the duration of immunity, I think the degree of boosting upon encountering chickenpox within the population if you've already been infected previously, etc. And so there you're adjusting those parameters to try to match the empirical data. So empirical data here is being used to judge and to evaluate model goodness of fit, and you're adjusting parameters. A little bit like a regression, but a nonlinear regression. And it's a regression that involves change over time from the model. Finally, one way that models can be used to interface with data that I don't have down listed here is models can serve as sources of synthetic data to, for example, test statistical models for their ability to, how well they function. For example, you could use a model to test administrative data algorithms. You have a model which depicts some hypothesized sort of health states in the population, their evolution over time, and you can using the synthetic population, the population from that model, you can apply an administrative data algorithm to that. Using data of the sort you would have through administrative data. Or you could attempt to apply an inference technique to that data that tries to infer some underlying features, and you could then judge it against the actual situation in the model, which is known. Kurt talked about that a little bit. He alluded to the fact that if we separate out how the healthcare system classifies someone on the one hand from their actual state on the other, we can sometimes we can use it to identify better ways that the healthcare system could identify people. So here, with parameter estimates, we are trying to estimate parameters in the model, either directly or via calibration, that will inform the model assumptions. Here, with data produced by the model, often for simulation models, the output from the model is not strictly just output. There's also feedbacks by which it's influencing behavior over time. So while there are output variables, there are also factors which are governing model behavior. So where do you get data estimates for these models? Well, one place you can get them is from surveillance data, from administrative data. You can estimate them with biostatistical methods. Potentially, you can, in some cases, get them from controlled trials, where the model will represent the factors that are not controlled in the trial, but in the community play a big role, such as compliance. There can be data from outbreaks that you try to calibrate to for the model. There could be clinical reports. Calibration to historic data is quite common. So models of this sort are some of their strongest, the goals for which people seek to use them, ladies and gentlemen, is to try to use them to ask about counterfactuals. But before we have confidence in them that they'll yield meaningful results for being used with counterfactuals, situations which haven't happened, we typically run them for some historic period where we know the situation and we see if they match the historic trends very well. If they don't match the historic data, the factual situation, we know what it is fairly well, we'd be naturally hesitant to try them for counterfactuals. So we run them and test them against historic data. We only parameterize them with data up to a certain year, and then we test if they can predict accurately what's happening in subsequent years, for example. Or we only give them a subset of data and see if they can predict others. We've made heavy use of administrative data here in the province. We're fortunate to have that, not always with the timeliness that one would hope, but we've made very heavy use of it. In other cases, for example, you can draw them from meta-analyses, systematic reviews of the literature. My colleague Kristen Hessmiller-Litch did a wonderful job with that with some of her modeling work about a decade ago with drawing from meta-analyses. Yes? Yeah. Yeah.
Does anybody ever rank those sources of parameter estimates? Is there a preferential ranking, or is it situation dependent? And a lot of times I've heard maybe just
It's a great question. So there's a lot of work that's been done, and I think in many ways very good work. And talking about the hierarchy of evidence in the context of evidence-informed medicine, and there's been nothing that I'm aware explicitly talking about this for models. What I do know is that modelers talk with modelers, and we do talk about those things, as you know, to each other, and there's certainly a preference for certain types of data. There's a sense of aesthetics that, I prefer not to rely on expert judgment if there's a better and more reliable source of data. But I'm not aware that people have formalized sort of that understanding or that advice, and that would be a gap in the literature. I mean, I want to be clear here that the number of modelers, the number of people who can undertake the techniques we're talking about here, worldwide in the health area is not a large community. We're talking about something which worldwide might, is in the hundreds probably, of people who are really quite capable of doing this sort of, really have good, very strong skills in this sort of model. People can dabble in it and can apply it a little bit, but for the folks who are advancing the methodology, really you talk about in hundreds. And I don't think there's been that attention to that hierarchy of evidence like probably there should be. And I think when it comes to dynamic modeling, there's some particularly interesting issues like the role that longitudinal data plays, which could really use some serious, intellectual attention. But I've heard it talked about informally, but never in a formal form. So I think that's a gap in the literature, and one where there could be contributions. A very important component of this sort of work is conduction of sensitivity analyses in UN, the next speaker here, together with Kelsey. We're very fortunate to have them here, and UN has done some fantastic work doing more rigorous sensitivity analyses in a very sophisticated fashion. Some of it conducted from Thorvaldsen building and some from Singapore. But using techniques to try to identify parameters that, according to how they strongly affect model results, but also the choice between policies. And I'd consider UN one of the few experts I know who's really thought through a lot of the issues here. And generally, there's opportunity costs, ladies and gentlemen. If you put your efforts into one thing in a model, often it means not putting it into another. You have to choose what to put in next when you're building it incrementally. And often we will put emphases on parameter estimation related to parameters to which the model exhibits high sensitivity. If it matters a lot to the model outcomes, we'll put emphasis into this. But not only that, ladies and gentlemen, this sounds like a weakness perhaps, but I'd say it's an asset. When we perform sensitivity analysis, these often give us much greater clarity about what our priorities are for data collection. And I've literally been in the situation of spending between $10,000 and $20,000 to collect new data from administrative data through the Ministry of Health with targeting particular parameters that are highly important in our model outcomes. So it allowed us to kind of focus our resource investment to things that really matter. Often here we're taking a model and we're matching it up simultaneously. This is quite different from normal regression against a single parameter, single dependent variable. Here we're often taking a given model and we're trying to keep it honest by having it simultaneously match a bunch of different time series. This from our work here with diabetes and end-stage renal disease in the province and its linked with gestational diabetes. And trying to match empirical data here in green and blue with sort of model results, gray and red, across many different time series simultaneously to develop confidence that the model that we have is quite accurate. Now, a central motivator for these sort of models is to examine counterfactual situations where we don't have data. The data generating process, to speak in statistical language, is going to change. We have data historically, which we can look back at from the current data generating process, but if we're talking about putting in place a new portfolio of interventions, or we're talking about a dramatically changed policy environment, here we might be dealing with a counterfactual situation where the data that's available in that situation is non-existent or very limited. So typically, before looking at those situations, because we can't directly assess its accuracy ahead of time there in a direct way, we develop confidence that it can predict some historic period results. Then we look forward and then we test it against actual results from the intervention. And we put in place metrics which will test it. I will tell you, since I started doing this work 15 or 20 years ago, I was awed when I first started getting into health modeling. I had gone, a decade before there in trying to address other decision-making issues elsewhere in sort of the social space. But when it came to health, I was awed by the amount of data. I was working in the States, and we could get data sets like the National Health Interview Survey, the National Health and Nutrition Examination Survey, the Behavioral Risk Factor Surveillance System, et cetera. And it seemed like amazing data until I heard a little bit about what went into some of the issues with it. People took me aside and said, well, you have to realize that's not very reliable. We all know that wasn't actually a very reliable survey for this. So I started to get a little bit more savvy. But one of the realizations that did come up here is that models sometimes allow you to spot inconsistencies in data. They allow you to spot problems in data that you otherwise wouldn't have realized. And there's been a couple situations in my life where I've taken a model, I cannot get the model to match the data empirically. I try up and down, left and right, and finally I go to the people who are experts and say, look, what's wrong with my model? And it turns out they say, well, no, don't worry about that. The data got redefined in that period. So, it wasn't your model that's at fault. It was because we were using a different definition for those years. Or they changed the definition of what was a preschooler for those years or what have you. So when it comes to empirical data, turning to instruments is important. But one thing I also found early on was that sometimes if you're thinking from a modeling perspective, it's not just that. If you're thinking from a dynamic perspective, trying to characterize the underlying processes that are going on, what you'll find is that a fair number of questions that are asked on standardized survey instruments are not nearly as helpful as you'd like, or a lot of the outcome measures that are reported for interventions aren't as helpful as they could be. You find that if only they had measured this, we would have gotten a lot more out of it. And this is one of the advantages for getting modelers to work together with folks involved in surveillance. Folks involved on the side of looking at outcomes of interventions as well. Syndromic surveillance, intervention-oriented surveillance. It's to make sure that those data items are collected, which can really help leverage the models. It can be really helpful and no more work for the folks involved in the instruments being formulated. I mentioned cross-validation. You will set aside some data when building and then use the data to assess it. I think I'm going to, because UN has arrived with Kelsey, I'm going to provide these slides. I'm not going to comment as much, but I think I will leave them for perusal. I can talk more about them after I come back. One thing I do want to emphasize is that model structure is often a key component of the assumptions that go into these models, not just the empirical data. Yes, the data is in there. Yes, the data points are in that model. Yes, you put in parameter values. But often some of the bigger assumptions of the model, the more fundamental ones, are in the structure. What's connected with what? What are those states someone can be in? What state can you go to from? You can go to state A. What can you go to from there? State B or state C directly? Those are often additional understanding that's incorporated in these models. Okay. The final comment I'll have is that models, even the best of models, the most detailed models, the most exquisitely worked on, empirically informed models, using only the best types of evidence, they're going to diverge from observed data. Why will they diverge? Because inevitably, ladies and gentlemen, there will be factors that they omit. There will be factors that are simplifications. There will be factors that are approximations, but also stochastics. There'll be factors that the model cannot reasonably include. Maybe it's aspects of economic performance. Maybe it's it's components of the of what happens weather-wise that causes some aberrations. Models will diverge from observations in the world at some level. What we are increasingly doing is taking models and putting them in a framework where they can be constantly regrounded as new data comes in, and kept current with the latest evidence, and then can be used to look forward. And I think that's one of the most valuable features of models. And be aware, when it comes to data, interventions change things. We could have a model that's most exquisitely tuned to existing data, but if we're entering a new policy regime, a lot of the things will be changing, and the model may be the least bad option for anticipating what's going on forward. Winston Churchill said about democracy once, it's the worst of all systems of government except for everything else. And I think so it is with models. Sometimes they're the worst of all ways to anticipate what's going to happen with counterfactuals, except for everything else. I don't know of an alternative. And certainly relying on our thinking and intuition is not proving very effective. Okay, so I think I'll pause my comments here on this. I'm glad to return to it if there's questions later. But I'd like to welcome with great anticipation Yuan and Kelsey for a presentation that they're going to make for their work together with the Ministry of Health project for the Edie Waits project. Do you want to come up to the front here? So Yuan and Kelsey, would you like to use your own computer? Is that the best way to do it? Okay, that's what I figured. Okay, so let me just stop this recording.